Modern maize appears to be one of the most successful plants on Earth. It grows tall, produces hundreds of kernels on a single ear, and is cultivated across enormous areas of the planet. There is only one small problem. It is remarkably bad at beginning another generation without human help. Wild plants usually release their seeds. The seeds fall, fly, float, or attach themselves to anything passing by. Maize does almost none of that. Well, it keeps hundreds of kernels locked together on a cob, then wraps the entire package inside layers of husk. An impressive harvest, a terrible escape plan. To continue efficiently, cultivated maize depends on people to open the ear, remove the kernels, preserve the seed, plant it again. So why does a plant so dependent on human hands exist at all? Because human hands made it this way. Its wild ancestor was teosinte, a grass from southwestern Mexico. Teosinte had small seeds, hard protective cases, and branches growing in several directions. As a wild plant, it was perfectly competent. As a corn cob, it was barely recognizable. Around 9,000 years ago, cultivators began selecting plants with more useful traits. No single farmer created maize. Generation after generation changed it, one harvest at a time. The crop began traveling before its transformation was complete. It crossed valleys, mountains, and eventually continents. Every new environment changed it again. So did every new culture, technology, and market. By the time maize reached the modern world, it had become almost unrecognizable. Teosinte was not an obvious candidate for domestication. Its seeds were small, each one enclosed in a hard fruit case. When the plant matured, its seed-bearing structures broke apart and scattered. This was excellent for a wild plant wants its offspring to escape. Anyone trying to gather dinner had a different set of priorities. Domestication began when people changed which plants were allowed to reproduce. They collected seeds from plants with useful differences. Some produced slightly larger kernels. Some had coverings that were easier to break. Some held their seed clusters together for longer. One choice made little difference. Thousands of growing seasons changed the plant completely. There was no blueprint for modern maize, and no one could see the final result. The process continued because each generation inherited a plant that was slightly more useful than the one before it. Over time, maize concentrated more of its growth into a central stalk and a smaller number of larger ears. The kernels became less protected. The cob became thicker. Most importantly, the mature ears stopped breaking apart easily. For farmers, this was excellent news. A crop that remained together was easier to gather, carry, and store. For the plant's independence, it was a serious career change. While teosinte could release its own seed, cultivated maize increasingly depended on people to perform that task. People gained a crop that was easier to use. The crop gained human beings willing to protect, transport, and reproduce it. The first maize breeders left no written manuals. Their archive was the harvest, and their notes were the seeds they chose to keep. More than 7,000 years ago, early maize was already moving through parts of Central America and into South America. It was not yet the crop later civilizations would recognize. Its ears were still small, its productivity was limited, and many domestication traits were still developing. In effect, farmers were carrying a work in progress. Every new landscape presented a different test. A plant suited to a warm Mexican lowland might struggle in a cold mountain valley. A variety with a long growing season might never mature. Farther north, rainfall changed, soil changed, altitude changed, day length changed. Fortunately, maize was traveling with people who knew how to observe it. Farmers selected plants that survived local conditions. In highlands, they favored maize that could grow under cooler temperatures. In dry regions, they preserved plants that completed their life cycle with limited water. In humid areas, they selected for an entirely different collection of pressures. Kernel color, hardness, starch composition, ear size, plant height, and growing time all began to diversify. There was no central office approving each new variety. Local farmers were conducting thousands of experiments at the same time. Most of those experiments left no written record. Their results survived as seeds. By approximately 4,000 years ago, maize had reached what is now the southwestern United States. Its arrival did not instantly turn every community into full-time farmers. Hunting, gathering, and the cultivation of other plants remained important. Over time, improved varieties, irrigation, storage, and farming methods suited to dry landscapes made maize more dependable. It appeared in parts of eastern North America during the final centuries before the Common Era. But widespread dependence on maize came much later in many areas near the end of the first millennium. CE arrival was only the first step. The crop had to be tested, adapted, improved, and accepted. That process unfolded at different speeds in different places. The presence of maize did not automatically make it a staple. For thousands of years, many communities consumed it only in modest quantities. Early maize was useful, but it had not yet taken over the menu. In some regions, that changed between roughly 4,700 and 4,000 years ago. As maize became a more important part of the diet, the transition depended on better varieties, more systematic cultivation, storage, and food processing knowledge. One of the most important developments was alkaline processing. Now widely known as neat, dried maize was cooked or soaked in alkaline water, often prepared with lime or ash. The process loosened the outer layer of the kernel, made the grain easier to grind, changed its texture and flavor, and increased the availability of certain nutrients, including niacin. The resulting maize could be ground into masa and prepared as tortillas, tamales, and many other foods. A field produced a crop. Knowledge turned the crop into a dependable food system. A seed can travel quickly. A complete cooking technology is much harder to pack into a bag. Maize was also consumed alongside beans, squash, chiles, fruits, greens, animal foods, and gathered plants. The success of maize agriculture was never the success of one miraculous ingredient. It was the success of an interconnected body of knowledge. As maize became more productive and dependable, dried grain could be stored between harvests. Surpluses could support larger populations and help feed builders, artisans, traders, soldiers, administrators, and religious institutions. Maize did not single-handedly create cities or states, but it supplied part of the food base that allowed increasingly complex societies to develop across Mesoamerica and other regions of the Americas. Its importance in daily survival also gave maize deep cultural meaning. In the creation narrative preserved by the Geisha Maya and the Popol Vuh, successful human beings are formed from maize. In Maya art, maize could be associated with growth, death, regeneration, fertility, and rulership. These traditions varied across regions and centuries, but together they show how thoroughly a crop could enter a society's understanding of human life. Maize was planted in fields, prepared in homes, and carried into stories about where people came from. Before the end of the 15th century, maize was an American crop. After 1492, it entered a rapidly expanding network connecting the Americas, Europe, Africa, and Asia. European sailors encountered maize in the Caribbean and carried seed across the Atlantic. From Spain and Portugal, the crop moved through Mediterranean agriculture, maritime trade, imperial expansion, and migration. This part of the story is sometimes told as though one ship delivered maize to the world. Jot's ships moved the seed. Farmers made it succeed. A newly arrived seed does not come with guaranteed success. Farmers had to learn when to plant it, whether it could mature before cold weather arrived, and which plants could handle unfamiliar rainfall, soils, pests, and hours of daylight. During the 16th and 17th centuries, maize spread through parts of Europe, Africa, Middle East, India, China, and Southeast Asia. Every region changed it again. European farmers selected maize capable of handling cooler climates and longer summer days. African farmers adapted it to tropical highlands, dry savannas, and humid regions. Asian farmers incorporated it into mixed farms, mountain agriculture, local cuisines, and animal feeding systems. In practical terms, maize was being made local again on several continents. New food traditions developed. In parts of Italy, maize became associated with, but across regions of Africa, it became the basis of widely consumed porridges. Elsewhere, it was roasted, boiled, fermented, milled, baked, and combined with local ingredients. But maize did not always travel with the full processing knowledge developed in Mesoamerica, where populations became heavily dependent on untreated maize and had little access to complementary foods. Niacin deficiency contributed to the seed had crossed an ocean. Part of the instruction manual had not. For most of maize history, farmers saved seed from their own harvests. Many varieties were open-pollinated, and farmers selected ears according to local priorities. Early maturity, large kernels, hard grain, sweetness, drought, tolerance, resistance to lodging, and suitability for food, livestock, or storage. The crop kept changing, but the people making those decisions were increasingly connected to distant markets. In North America, corn became closely tied to livestock production. Grain was difficult and expensive to transport over long-distance seas. Animals could convert it into meat, milk, fat, power, and other products. Corn was also ground into meal, distilled into whiskey, and stored for winter. As canals and railways expanded, a crop once shaped mainly for local use was increasingly judged by weight, grade, price, and consistency. The kernel was acquiring a resume. Mechanization accelerated production, improved planters placed seeds in more regular rows. Mechanical shellers separated kernels faster than hand liver. Railways connected farms with mills, livestock centers, cities, and ports. Meanwhile, seed selection entered universities and agricultural experiment stations. Farmers had always known that parents affected the next generation. Researchers began turning that practical knowledge into controlled crosses, recorded trials, and statistical comparisons. During the early 20th century, breeders produced inbred maize lines through repeated. The individual inbred plants were often small and weak. This was not an encouraging first impression, but when carefully selected lines were crossed, their first-generation offspring could display hybrid vigor. They often grew more strongly, produced more dependable yields, and matured more uniformly. For mechanized farming, uniformity was extremely useful. Machines prefer plants that keep appointments. Hybrid adoption in the United States was remarkably rapid. In 1935, hybrids covered only about 1% of corn acreage. By 1940, the share exceeded 30%. By 1960, hybrid seed accounted for approximately 96%. That was an important condition. Seed saved from a hybrid harvest did not reliably reproduce the same combination of traits in the next generation. Farmers seeking the original performance generally purchased new seed. The relationship between farmer and seed changed. Hybrids also worked as part of a larger system. Tractors, mechanical harvesters, fertilizers, crop protection, irrigation, public research, private breeding, transport, and government policy all contributed to rising production. The modern high-yield cornfield was not created by one miraculous seed. It was created by an entire production system. Industrial processing changed the question asked of a corn kernel. For most of history, people had asked, what food can be prepared from this grain? Industry asked, what can this grain be separated into? Wet milling divided the kernel into starch, germ, fiber, and protein. Dry milling produced meal, flour, grits, cereal ingredients, and brewing materials. Oil could be extracted from the germ. Protein and fiber could enter animal feed. Starch could be thickened, fermented, modified, or converted into sweeteners and other materials. The kernel had stopped being one product. It had become a small industrial department with several employees. High-fructose corn syrup entered the American food supply in the late 1960s, and during the 1970s, expanded rapidly. Improved enzyme processing methods made large-scale production more economical, giving food and beverage manufacturers a liquid sweetener that was easy to transport, easy to blend, and easy to use. Energy created another pathway. Interest in corn-based ethanol rose during the oil disruptions of the 1970s. Production later expanded through technological improvement, market incentives, and public policy. The United States established a renewable fuel standard in 2005, and legislation in 2007 expanded the program. Corn was now moving not only into kitchens and livestock systems, but into fuel tanks. The process also produced distillers' grains that could be used as animal feed. Industrial systems rarely move in one simple line. They create branches, byproducts, new markets, and new dependencies. A further change arrived through genetic engineering. In 1995, the United States Environmental Protection Agency registered the first Bt plant incorporated Commercial Bt corn varieties followed in 1996. Other engineered varieties were developed to tolerate specific herbicides, and later seeds combined several traits. Genetic engineering did not replace conventional breeding. Breeders continued crossing plants, evaluating offspring, and selecting useful combinations. Molecular markers made some choices faster. Biotechnology introduced particular traits. Newer methods increased the precision of certain changes. The goal remained familiar, influenced the next generation. The tools, speed, scale, and ownership systems had changed dramatically. By the middle of the 2020s, genetically engineered varieties covered more than 90% of American corn acreage. A crop first shaped by early farmers in Mexico had entered an era of laboratories, patents, regulation, and global seed markets. 9,000 years separate teosinte and modern maize, but the distance between them was not crossed in one great leap. It was built from countless smaller changes. Early cultivators in southwestern Mexico selected plants that were easier to gather and more useful as food. Farmers across the Americas carried the crop into new environments and continued changing it. Communities developed farming, storage, and processing methods that turned maize into a dependable staple. After the 15th century, farmers in Europe, Africa, and Asia adapted it again. Later, breeders developed hybrids for mechanized agriculture. Industry separated the kernel into food ingredients, animal feed, sweeteners, alcohol, and fuel. Modern biotechnology added new tools. Each stage changed the crop, but no stage began from nothing. Most of the people who shaped maize left no written account of their work. Their names were not preserved. Their experiments survived in the crop itself. A larger kernel, an earlier harvest. A plant able to grow at a higher altitude. A variety that survived drought, cold, insects, or disease. No single farmer created maize. No single civilization completed it. The history of maize is not the story of one plant suddenly conquering the world. It is the story of people changing a plant slowly, repeatedly, and often without knowing what future generations would do with the result. Civilizations are often remembered through monuments, rulers, and wars, a field observed carefully, a useful difference recognized, and one seed saved for another season. 9,000 years ago, the first choices were made. The harvest is still continuing.